So let's say that we have a problem like this, where we're taking that 4, we're plugging it in for x as sort of our first stab at it. And what we get is that 4 squared minus 16 and 4 minus 4 gives us 0 over 0. Well, if we look back at our limits to notes, we saw that 0 over 0 creates a removable discontinuity. The limit's going to be a number. And this lesson is our time to go and figure out exactly what that number is. So at the end of this lesson, you should be able to find limits when there is the indeterminate form, both using factoring and L'Hopital's rule for the real stumpers. So this implies or indicates there's a removable discontinuity like that. Basically, there's just a little place where the y value is not existent, but overall it's a smooth curve except for at that one point. And as the name implies, a removable discontinuity can be removed to allow us to determine what the function wants to be, what value it wants to have at that point. We remove a removable discontinuity by manipulating the expression until something cancels out. You see, for each function that has a hole or a removable discontinuity in it, the function behaves just like a function without that hole, except at one point. So if we can find the equation that behaves like the function with the hole, we can then substitute for x to find the limit. For example, let's look at x plus 4 versus x squared minus 16 over x minus 4, which if we factor this, we see it's x plus 4, x minus 4 over x minus 4. And these x minus 4 and x minus 4, this cancels out for every value except 4. And so what's going on is that this function, right here, y equals x plus 4, let's see, it's just a line like that. And then this one is exactly the same because when x is 3, when x is 2, when x is a million, these two are going to be exactly equal to each other and cancel out. But when x exactly equals 4, it's undefined because we're not allowed to divide by 0. Oops. However, we can see that when x is 4 over here, we can see what the function wants to be and what it would be if that removable discontinuity weren't there. So the idea for this piece that we're learning how to do is that we basically just want to find something and cancel it out. Because when we cancel it out, we're going to get a function that is just like the one that we have, except for that whole or removable discontinuity is gone. So we're going to start off with removing wholes by factoring. First, check to make sure that you need to do anything, because remember, some of these you just have to plug in the numbers and they work out just fine. These ones aren't going to because they're obviously in the section of the notes where we're practicing this new technique, but it's always important to check just because when you're actually looking at a real problem, you don't always need to use these techniques. So this is removable discontinuity. So let's factor. Something's got to cancel out, and then we're good to go. So this is going to equal limit as x approaches 5. Let's factor the numerator, factor the denominator. Negative 30, positive x, that's x plus 6, x minus 5, which makes sense. One of them should be in the bottom because we want it to cancel out. And so we can cancel because we're not evaluating it at 5. We're saying as we get really close to 5, but not exactly at it. So this means this behaves like the limit as x approaches 5 of x plus 6. Now we can just plug that in, and there's our limit. If we didn't have that whole, that removable discontinuity, the function would be equal to 11 when x was 5. So that's the gist of it. Let's do a few more examples like that. Again, always check that you need to. So negative 3 plus 3, negative 3 squared minus 9, that is indeed 0 over 0. So it's going to be the limit as x approaches negative 3. Let's factor this. Okay, so we just have to plug that negative 3 in there. Once we've got a number, we're happy. Sometimes our factoring can be a smidgen more complicated. there, rather than doing our normal diamond or box method, we can just factor out common factors. First, though, we should check and make sure that we need to. So if we put in 0, we have 3 times 0 cubed plus 5 times 0 squared. 9 times 0 cubed minus 20, 0 squared. That emphatically equals 0 over 0. So we should see if we can factor and cancel. So I can factor out an x squared. That leaves me with 3x plus 5. I can factor out an x squared here, which leaves me with 9x minus 20. These cancel out, so this is a limit as x approaches 0. 3x plus 5 over 9x minus 20. Now when I substitute that 0 in, it's not such a big deal. 3 times 0 plus 5 over 9 times 0 minus 20. Those subtract to be 0, so we just have 5 over negative 20, or negative 1/4. So that's the general idea of it. Sometimes we have to massage the equations a little bit before canceling. So some adding or subtracting or combining of like terms kind of thing. So let's look at this one. Limit as, let's say another variable. Let's say h approaches 0. It doesn't always have to be x. Let's say we've got 5 x plus h minus 5x all over h. Notice this x is just along for the ride. We'll see what happens to it. This h is going to be 0. And we notice that if we just plug it in, we've got 5x plus 5h minus 5x over h. If we plug 0 in for h, we're going to get, let's see, so this is 0, this is 0. 5x minus 5x plus 0 is 0, so it is indeed 0 over 0. So right now we're not seeing anything that really cancels out terribly well here. But let's see if we can just sort of distribute and combine like terms and see if we can get anything. So let's distribute this 5x plus 5h minus 5x all over h. 5x minus 5x is 0, so we just have 5h over h. Oh, looky there, that cancels out. Limit as h approaches 0 of 5, or just plain old